There are two ways of the graphical representation of the above mentioned frequency function Wj omega. So just a very short recap at the very beginning here. So Wj omega is called the frequency function, or the other notation is here W bar and omega. But in the lectures I mainly use the first one, Wj omega. How to get it? We have to divide the complex amplitude of the output function, the response of the system, and the input, the feeding sinusoidal complex function. That is, at the end, we are going to get a function k. This function is denoted by the amplitude function, and we are going to get another function. It is denoted by phi. This is the phase function. K and phi are depending on the frequency omega. There are two ways of the representation. The first one is called the Nyquist diagram. In this video I am going to define the Nyquist diagram, and the second one, in the next video, we are going to speak about the so-called Bode diagram. So what is the Nyquist diagram? The Nyquist diagram is the so-called polar diagram of Wj omega, that is the frequency function in the complex plane. Because the frequency function consists of two functions, the amplitude function and the phase function. The Nyquist diagram represents these two functions together in one function in the complex plane. This is the complex plane which I draw, and this is the real axis, the imaginary axis. But what? The real value of W bar, the complex function, and the imaginary part of W bar. How to get it? From frequency to frequency, we are going to get k omega and phi omega. So every frequency we have got a value for the amplitude and we have got a value for the phase. For example, let's say omega equal to 0 and the phasor is going to point to here. This is omega equal to 0. Next, we are going to increase omega, and we are going to get a value like this one. So our phasor is going to point to here. This is omega 1. First one is omega 0. Okay, and then we are going to get the higher omega, omega 2. So omega 2 is like this one, omega 1 is bigger than omega 0, and so on and so on. So we increase omega, and we are going to get some values on the complex plane. Typically, it is going to decrease and going to go to the origin. So we are going to get some points on the complex plane if the omega is increasing from 0 to infinity. And the next, we are going to connect these points from 0 to infinity. So it's easy to see that it can be a very large work to get the Nyquist diagram, because we have to calculate Wj omega at many frequencies. We have to put these values to the complex plane, and finally we have to connect these nodes. Nyquist diagram can be mirrored to the real axis. So it will be something like this one. Okay, and omega is 0 here. Omega is increasing in this direction. Omega goes to 0 at this point. But sometimes, especially for the stability analysis, please remember that we are going to come back to Nyquist diagram as stability analysis, and sometimes at the design of PID type controllers. And in that case, we need the complete Nyquist diagram. Complete means that our omega is running between minus infinity to plus infinity, but of course physical meaning has only for positive omega. It is denoted by the red curve. The green curve is for the omega between minus infinity to 0. So this point is minus infinity here. Omega is increasing in this direction. Omega is 0 at here, and omega is increasing to plus infinity. But it is enough to obtain the Nyquist diagram for the positive omegas, and then the diagram can be mirrored to the real axis because of this property of the Nyquist diagram. So we are going to come back to here at the stability analysis and for the PID controller design. In the next video, I am going to show you the Bode diagram.